In lesson 10.3, we're going to continue talking about ways to write vectors. In fact, today we're going to talk about how can we write a vector in component form if we know its magnitude and direction. So let's do a little bit of review from trigonometry. So when we were talking about angles in the unit circle and the coordinates of the points, we drew this diagram quite a bit. So we said, here's your x and y axis, and here we have an angle theta. And to get to the point where this terminal side ends, we said, well, if this has coordinates x and y, that means we go over x and we go up y. Now, a bit ago I said if we were in the unit circle, but we don't have to be in the unit circle, so we called this the radius. Sometimes the radius is 1, and sometimes it's not. Okay. So in this diagram, I've got the three sides labeled x, y, and r for the radius, and then we've got our angle, theta. So I'd like to take a look at the sine of theta, right? Using our SOHCAHTOA, the sine equals y over r. Well, if I multiply both sides by r, I get y equals r times the sine of theta. And when our radius was 1, we said y equals the sine of the angle, right? So that's, we know that. We've been using that a lot. Let's do the same thing with cosine. In this angle, cosine equals the adjacent over the hypotenuse, so x over r. But if I multiply both sides by r, I get x equals r times the cosine of theta. Okay, so those are relationships that we talked a lot about in Algebra 2 and again earlier this year. We are going to relate that to vectors, because remember, vectors is just a bunch of right triangle trig. So suppose we've got this vector. You can see now instead of having a point at the end, I have an arrow at the end. And when we talk about the components, we said from the starting point we're going to go over our horizontal component, and then our vertical component is b. This is the direction, and the length is what we call the magnitude. So if we have vector v, this side is the magnitude of v, or the length of vector v, just different notation. Well, I'm going to do something similar. I'm going to come up here to the top right corner and do the same thing we just did. I'm going to say, all right, well then what's the sine of theta? Sine of theta equals the opposite, b, over the hypotenuse, which is the magnitude. And I can do the same thing with the cosine of theta. I need the adjacent over the hypotenuse. So if I wanted to solve for a and b, the components, I could multiply both sides by the magnitude on both of these. It just looks a little cumbersome because of the notation. So now I'm left with b equals the magnitude times the sine of the direction, while a equals the magnitude times the cosine of the direction. So the idea is if we are given the magnitude is the absolute value of v, and the direction of the angle is theta, we can put the vector in component form. The horizontal component is the magnitude times the cosine of the angle. The vertical component is the magnitude times the sine of the angle. Just some right triangle trigonometry. Okay. All right. So let's go down here. It says find the component form of vector b.
If any staff member is available to cover a first period, please let Heidi know at 6204. If you're able to cover a first period class, please let Heidi know, 6204.
Sorry. So it says find the component form. Remember, component form looks like this. The magnitude is 12. The direction, or the angle, is -30. Well, we have a formula for that. We need the magnitude times the cosine of the angle. Then we need the magnitude times the sine of the angle. That's what we just came up with on our last slide. Well, now it's up to us to clean this up a little bit. So let's maybe draw this chart. We're going to use it a couple of times. We need to find some trig values. So let's see. I'm going to go down the left side. We've got sine, cosine, tangent. We've got from smallest to largest, 30, 45, and 60. And we'll just fill it in. Remember, we did our 1, 2, 3, 3, 2, 1. Take the square root of everything. Divide them all by 2. I'm not going to fill in the bottom column, or I'm sorry, the bottom row, because there's no tangents in here. If we need to, we'll do it later. Now, -30 degrees is in quadrant 4. And in quadrant 4, cosine is positive, sine is negative. So let's see, we've got 12 times something, 12 times something. The cosine of 30 degrees is radical 3 over 2, and in the fourth quadrant, it's positive. The sine of 30 degrees is 1/2, but in the fourth quadrant, sine is negative. So let's just clean that up. 12 divided by 2 is 6, so I'm left with 6 times radical 3. 12 divided by 2 is 6, so I'm left with -6 times 1. So again, we've taken a vector with a magnitude and a direction, and we've put it in component form. Okay, good. Let's take a look at the next one. Same thing, find the component form for vector R. I guess we could have labeled this. This is vector B. Find the component form of vector R, whose magnitude is 15, bearing is 210. Okay, we must be very careful with that. First, we want to change that to a direction. So let's go draw our picture. If the bearing is 210, that means we're starting up north, and we're going to go clockwise. There's 180, there's 210, which 30 degrees is in here, isn't it? Well, remember, we measure angles either negative here, or we go around this way. I'm going to go around this way. So if this is 30, this is 60. So this is 180 plus 60, which is 240. Pictures help, right? We've said don't try to memorize a bunch of stuff, just use a picture. All right, so notice I'm in the third quadrant, so 240 degrees is in quadrant 3. Sine and cosine are both negative there. All right, so here we go. We've got a rule. It says take the magnitude, multiply it by the cosine of the angle, then take the magnitude and multiply it by the sine of the angle. Now we're just cleaning it up. So I've got 15 times something, and then 15 times something. Again, 240 degrees is in the third quadrant. Cosine and sine are both negative. And I love that I already have this. This is 60 degrees. That's my reference angle. Remember, reference angles get measured up to the x-axis, so I'm looking here. So I need the cosine of 60, which is 1/2. And then I need the sine of 60, which is radical 3 over 2. Let's clean that up. So let's see, vector R is -7.5. If you want to use decimals, you could leave it as 15/2. And then let's see, I guess I should have left it, but how about -7.5 radical 3? So again, I could have written -15/2 and -15 radical 3 over 2. So decimal, fraction, either way. Okay. All right, let's take a look at this next one. It says, write a vector in unit vector form, underline, box in. Remember, unit vector form uses i's and j's. Well, that didn't really change anything. We still need A and B. Whose direction is negative 145 degrees and has a magnitude of 11.5. And they're telling us we're going to use a calculator. So, all right, well, let's start with component form, I think. So we need the magnitude, which is 11.5, times the cosine of the angle. Then we need 11.5 times the sine of the angle. Now, again, that's going to be in component form. That's okay. I'm grabbing my calculator. I'm just going to go type this in. We need to make sure we're in degrees. I should still be in. Perfect. And I've got 11.5 times the cosine of negative 145. I'm sorry. I missed my negative. Turns out to be the same thing. So I get negative 9.420. And then I need 11.5 times the sine of negative 145, which is negative 6.596. So that's my component form, but they asked us to use unit vector form. Not a big deal, let's just tack on some i's and j's. So I've got negative 0.42i minus 6.596j. Great. So in this math notes box on the back, we've said everything, so it's just kind of putting everything into one place. A big thing, we said this, for this formula, the angle must be in standard position and not a bearing angle, okay? All right. Excuse me. All right, so next slide. Given vectors v and u. V equals 2i plus 3j, and u equals 3i minus 2j. It says determine if the vectors are perpendicular. Oh, well, let's take a look. Let's draw them. I gave us a starting point. So we're going to go, I'm going to do vector v first. So I'm going to go to the right 2 and up 3. So there's vector v. And vector u, I'm going to start in the same place. I think it's going to be easier to look at it. I'm going to go to the right 3 and down 2. It says determine if the vectors are perpendicular. Well, they look to be perpendicular, right? It looks like we've got a right angle, but we can't just go by looks now, can we? So let's think about what it means to have perpendicular lines. Remember how perpendicular lines have opposite reciprocal slopes? Now, I know these aren't lines, but they're line segments, so we can still think of the slope. So I'm going to say, what is the slope of vector v? Well, we're going up 3 and right 2. What is the slope of vector u? Again, slope is vertical first. I'm going down 2 and right 3. Are they opposite signs? Yes. One's positive, one's negative. Are they reciprocals? 3/2 and 2/3? Yes. So, yes, these two vectors are perpendicular. However, in the world of vectors, we don't say the word perpendicular. Perpendicular vectors are called orthogonal. Means perpendicular, it's just a different word. Orthogonal vectors are vectors that are perpendicular. Okay. All right, so this one says write a vector that is perpendicular to vector b, and b is I plus 7j. Well, let's think about this for just a second. The slope of vector b, we want the vertical, right, rise over run. This is the vertical component, it's a positive 7, and then the run is a positive 1. So my slope is 7. Well, something perpendicular or orthogonal would have a slope of negative 1 over 7. All right, well, so let's write that. Let's call it vector C. I don't know, I just picked a letter. So that means I want the vertical component to be negative and the horizontal component to be positive 7. So I have 7i minus 1j. And we could certainly use the grid. This grid is not big enough, I don't think. But we could certainly use a grid to kind of play with that and check it, okay? But then my question is there more than one answer to part C? Is this the only vector that is orthogonal? And let's look at even our picture in part A. I started with vector V and vector
Quick
U.
interruption. Bus 104 was late again today. Bus 104 was late again today.
Vector U is orthogonal. It's not the only one. What if I had gone the other direction? Right, I'm going to turn my paper just for a second. What if oh, that's not very great, but what if I had that picture? Not great, I know, sorry. Well, think about this one went down 2 and right 3. This would have gone up 2 and left 3. The negative is just in the bottom instead of in the top, but we know it still means the same number. So like here, if I had a negative 1 over 7, it could have just as easily been 1 over negative 7. So we could say, yes, there is another answer, and how about we do negative 7i and a positive 1j. Okay. We can always draw a picture, can't we? All right. So let's take a look at this last one. It says vectors are used to represent physical quantities. For example, force. Force has both a magnitude and a direction. So suppose you are mowing a lawn on flat, level ground, and you're pushing along the handle of the mower with a force of 50 pounds. The arrow we're about to draw will show our push. All right, so let's draw a little picture here. And by the way, suppose the handle of the mower makes an angle of 45 degrees with the ground. All right, I'm even going to get out a green marker for my grass here. All right, so here's our grass. Flat, level ground. My lawnmower at home is red, so I'll use my red pen. So we've got our lawnmower down here. You know, it's got some wheels on it. And then it's got its handle. And it says the handle makes an angle of 45 degrees with the ground. All right, so you know what? Here's me. I'm even mowing my grass. Okay. Oh, except I'm flying. Give myself some longer legs. Okay, so there we are mowing our grass. Lovely picture. So when we push along the handle, here's the handle, we are pushing down along the handle. They're telling us that our force is 50 pounds. And the handle makes an angle of 45 degrees with the ground. Awesome. Okay, so we just did draw a vector diagram to illustrate this situation. Okay, so it's a little more of a picture and not as much of a diagram, but the vector is going down to the ground. It is 50 units long. Okay, it says resolve this vector into horizontal and vertical components. Component form, right? We can turn this into component form. That's what we spent the whole front doing. We have two choices. We can either use the formula from the front, or we can just draw the picture and go with it that way. Completely up to you. To get from here to here, we can go over and down, or we can go down and over. It doesn't really matter, does it? In this picture, it doesn't matter. So we've got my 45 degrees here. Oh, hold on. Hello? Hi. Sure. Yep, I can do that. Yep, I can do that. You're welcome. Thanks. Bye-bye. All right, sorry, there's no pause button on my record. Okay, so we've got our 45, our 90, which means we've got another 45. The hypotenuse is 50, so it's I know the picture doesn't show it. It's not to scale, but I've got a 45, 45, 90. And I know the hypotenuse is 50. And remember, to go from a leg to a hypotenuse, we multiply by radical 2. So to go backwards, I'm going to divide by radical 2. So to get from here to here, I go over 50 over radical 2, and then I go down 50 over radical 2. I'm going to turn those into decimals anyways, and you might have used the trig. And that's fine too. 50 divided by radical 2 gives me 35.355. So I have 35.355 comma negative 35.355. Okay. So then we get to question C, and it says, which component, the vertical or horizontal, is doing the useful work of moving the lawnmower ahead? Well, let's go back to our picture. Maybe I'll even draw it this way. To go from my hands to the mower, we can go straight there, or we have this vector added to this vector. There's my vertical component, there's my horizontal component. If I'm pushing the mower forward, this is the vector that's going forward. So the horizontal component is what's moving the mower forward. So question D says, if, this is a funny question, if there was an easy way to get down to the ground level and push the lawnmower horizontally, thinking kind of like army crawling along the ground, how much force would need to be applied to continue moving the mower at the same rate? So again, with the handle, we were having to use a force of 50 pounds because part of that force was going down and part of it was going over. But if we could just get down on the ground and push the mower horizontally, how much force? Well, we're looking at that component of 35.355 pounds. That's the force that's moving it forward. Okay, a ridiculous picture, I know. Ridiculous question. The point is we have to use more force because part of that force is going down.